Hi everyone. Today we're going to kind of change gears. And on a bunch of the previous days we've been dealing with trig functions. And what we're going to introduce is the idea of a trigonometric identity. And so what you'll see on the screen, the definition of what an identity is. And I don't necessarily always think that red definition makes the idea of an identity clear to you. But an identity is a mathematical statement that is true for all values of the given variables. And so if we were to try to kind of reword that idea then, what conclusion we really draw is that the value of the variable doesn't matter. Since it's true for all values of the variable, then we can almost ignore the variable to some extent. Now, as I said, I don't think that really clarifies the issue for us. So what I want to do is I want to kind of jump into something that's going to look a little weird, but I think that it might really address the concept of an identity. And so what you'll see on the screen right now then is just an instruction to solve, and we have 3 equations. So for us to go through, by no means do I think any of these are difficult, but it is to talk about an idea. You guys could go through and solve the first equation and get x equals 2. Now, why is that the solution to that equation? Well, it's because if you were to replace the variable with 2 on the left side, then your left side equals your right side, and since your left side equals your right side, then therefore my solution is 2. It proves that solution. That's us in grade 9 going back, learning how to solve, and learning what the meaning of a solution is. Well, if we were to jump into B then we may go through, and let's just say that we put the blinders on and we went through to solve that. Then we may get to something like this. Or we may even get to something like this. And in either case, we should see something important. In the first green line, that says 0 times some number gives you 0. And well, 0 times any number gives me 0. So my solutions for x would be any number. Or you take a look at the last green line, and if we were to answer the question, does 0 equal 0? Then we should answer yes. And when does 0 equal 0? The answer would be always. And so therefore, what we end up getting is a solution that x could be any real number. That being said, the left side always equals the right side, regardless the value of the variable. So if I was to stop real quick and just address these 2 cases, what we have in A is an equation. The left side equals the right side for a limited number of solutions. However, what we have in B is we have an identity. That is, the left side equals the right side regardless of the value of the variable. So, what are we really talking about then with an identity? Maybe we have a better sense of it in B. I think, though, we may be looking at it and going, yeah, but what's the point? I can see that x plus 3 always equals x plus 3. Why would anybody ever write that? Well, take a look at problem C. And we may get a better sense then of what an identity is. Notice very quickly that your left side of that equation is 8x plus 12. The right side is 8x plus 12. So we can see then that this is an identity. The left side expression is the same thing as the right side expression, and therefore the left side will always equal the right side regardless of the value of the variable. However, in the first line we notice they didn't look equal. They looked different. So, what are we going to get into as we study trigonometric identities? Well, we're going to get into instances like C, where we've been given an identity we just don't know we have. And it'll be our job to prove that it's an identity by making the left side look exactly like the right side. So, I still don't think we have a great sense of where we're going with it yet. But to be able to get in and work with identities and to eventually prove them, we need to have some tools with us. So what we want to examine now is a couple tools we can use to work our way through this process. The first tool that we're going to have is this identity that states that tan theta is equal to sine theta over cos theta. What this is actually known as is your quotient identity. It's quotient. Quotient means division. Notice I can replace tan with the division of two ratios, sine over cos. Now, if we're going to use an identity, then we have to prove it first. So we have to prove it ourselves to ensure that this green statement is always true regardless of what angle theta is. So that's what it says. It says that the tan of any angle is equal to the sine of that angle divided by the cos of that angle, regardless of the angle. So much so that when you guys start to use the quotient identity, you'll probably even stop saying theta. You'll just say tan equals sine over cos, because the angle doesn't matter. So, as I said, for us to be able to use it, we got to prove it. So, how are we going to prove it? Well, the way that we can prove something is equal is to break it apart, just as you did back in grade 9 to prove the solutions to an equation. So, we are going to take the left side, that is tan theta, and we are going to take the right side, which is sine theta over cos theta. And if we can independently manipulate the appearance of those and show that left side looks exactly like right side, then we have proven that tan theta equals sine theta over cos theta. So, I don't think we're at the point where we can prove stuff on our own yet. So, let's kind of walk through this one together. What we can do to be able to go through and prove this is we can go right back to our basic definitions for SOHCAHTOA. I have 3 trig ratios here, and I know how to calculate each one of those trig ratios. So let's take that left side. We have tan theta. Well, how would you calculate tan theta? Well, for us, we know tan is the opposite over the adjacent. Okay. That didn't really help me much. So what I'm going to do then is I'm going to jump over to the right side, because I know how to calculate both the sine and cos of theta. That I know that sine theta would be my opposite over my hypotenuse, and my cos theta would be my adjacent over my hypotenuse. Now, what I have in that expression is the division of 2 fractions. And I can actually simplify that, because I know that to go through and divide fractions, I can flip and multiply. And so as I multiply by that reciprocal, I also notice that I'm going to have a common factor of the hypotenuse that could divide out. And when I do simplify that, I'm going to simplify that to the opposite over the adjacent. And I want us to notice right now that our left side expression looks exactly the same as the right side expression. Notice we did it independent of each other. At no time did I use the equal sign to prove that they were equal. And by manipulating each side independently and arriving at the exact same expression, I have shown that left side equals right side, and therefore I have proven that identity. So I know that tan of theta equals sine of theta over cos of theta, or tan equals sine over cos. And that becomes the first tool that I need to have memorized. I need to know that cold to be able to help me work my way through proving other identities. So let's jump in and let's try to develop a second tool for us. And so what you'll see on the screen now is going to be our second tool that we're going to use. This is another trig identity. And this one, I'm going to kind of hold off on the name for it. What we're going to do is we're going to work our way through this identity. And we need to know that to use it, we got to prove it. So somehow we have to prove that the sine squared of some angle plus the cos squared of that same angle is always equal to 1. Okay, so how can we do it? Well, last time we worked our way through dealing with our basic SOHCAHTOA definitions. And what I'd like to do this time is I'd like to work our way through dealing with a bit of a geometric proof. So for that, we can go back to our rotation angles. So let's imagine we've got our set of axes, and we are going to draw, just for simplicity's sake, a terminal arm lying in quadrant 1. And it goes through some generic point P, which would have the coordinates x, y. Well, some people, just out of instinct, might be able to then say, well, I know that I could always drop in a height, which would enable me to label this bottom side as x and this top side as y. Now, I'm going to go through and label that third side on that triangle. It might surprise you to what I'm going to label it as, but I'm going to label it as an R. Now, why would I label it as an R? Because I want you to imagine that if I was to take point P and rotate it, that it would allow me to create a circle. And what would the property R be of that circle? It would be the radius. So that's why I'm choosing to label it as R. It really doesn't matter though. Okay, what I can then use rather than SOHCAHTOA definitions is I could go through and I could use my X, Y, R definitions to try to prove this identity. So the first thing I need to do to prove an identity, I need to break it apart. So I'm going to take the left side that was sine squared theta plus cos squared theta. And then I'm going to take the right side of 1. They are broken apart. They will never touch each other. Okay, now I can use my diagram to substitute in values. I see in that diagram that my sine squared, well, sine is opposite over hypotenuse, so that is y over r. Now, that says sine squared, so I know I need to square my whole ratio. My cos squared would be my adjacent over my hypotenuse, and that's also squared. Okay, I made a substitution of something in there. My next action I'm going to follow is to try to simplify that. Well, I can square the first fraction, and I can square the second fraction. Well, now I need to add those two fractions together, but the nice part is that those two fractions already have a common denominator. And now maybe I hit a bit of a snag. I need to somehow try to make that fraction look like the right side. But maybe I'm a little bit stumped on it. However, for some of us, we're going to take a peek at that solution and we're going to kind of go, maybe I can see a way that I could manipulate that. I'm going to jump over underneath the diagram right now, because if I take a look at that diagram that I created, it's a right triangle. And the other tools that I have disposal aren't just trigonometric tools. It's not just SOHCAHTOA. But if we go right back to dealing with a right triangle, the first thing that we should be thinking of should always be Pythagorean. And notice that x squared plus y squared is equal to r squared. And if that's the case, then I can substitute it in. So what I'm going to do is I'm going to sub in that r squared equals x squared plus y squared. And if that's the case, then when we look at the top of that fraction, we have y squared plus x squared. That would be the same thing as x squared plus y squared, and therefore we could replace it with r squared. Well, now that I subbed in, I can simplify that, and r squared divided by r squared is always equal to 1. And now that I made my left side look like my right side, I have now proven that identity. And so, I know that sine squared of any angle plus cos squared of any angle, as long as those angles are the same, has to always equal 1. And maybe you can see why the name of that identity is the Pythagorean identity. So, you now have your two tools. You have your quotient identity, you have your Pythagorean identity, and those are the two tools that we can use to be able to go through and solve other identities. So, what you'll see on the screen now is going to be the instruction that we're going to follow for the next couple days. The only instruction you're going to see is prove. Now, what do we mean when we mean prove? Everything that we just did. Prove that that left side equals the right side. That the left side is always equal to the right side. Secondly, you could also see the instructions that would say show, because show that would be the same thing as prove. So, the first thing for us to do to be able to prove anything is to break it apart. And so, I need to try to show that 1 over cos x plus tan x is the exact same thing as 1 plus sine x over cos x. So, let's walk through this one together because we are still brand new to proving trig identities. Okay, I have two tools at my disposal. I know that regardless of angle, tan x is always equal to my sine x over my cos x. I have my quotient identity. And I also know that the sine squared of any angle plus the cos squared of any angle equals 1. These two tools I'm going to try to use to manipulate the way trigonometric expressions look. And hopefully over time, one of the first instincts that you're going to build up is that if you see tan in an expression, replace it. Replace it with what it's equal to. And so, if I was then to manipulate this first expression, because I see my tan x, I know that tan x is always equal to sine x over cos x, then I can replace that. Now, I didn't go through and develop that proof. Somebody else did. And so what we can do is we can kind of quote that the same way you would cite something in an essay. I just used my quotient identity, so I'm going to put a little Q and circle it off on the side. That tells my reader why my expression changed. Well, every time I sub something in, my next decision is made for me. Every time I substitute something in, my next action is to simplify. So, I'm going to simplify my expression. I notice I have a fraction plus a fraction. Those fractions have a common denominator. And so I can simplify it. And right there, I have done my job. I have my left side looking like my right side. And I've done it independent of each other. Therefore, my left side equals my right side. I have proven it. There you go. That's proving a trig identity. Now, to be very honest with you, that's about as easy as they will ever come. So let's start to work to build up our instincts of what to try as we have to go through and prove. So what we'll see in B is another identity we have to work our way through and prove. Your job moving forward is to try every single one of these identities on your own first. The only way that you get better working with identities is to gain experience. You need to train your gut to tell you what feels good, what feels like a good decision, what feels like a bad decision. And the only way to do that is to kind of take some bad routes that you go through and you make a decision and you follow it through, and then you figure out that it didn't lead you anywhere. And so you start to build up an instinct then that, well, that wasn't a good thing to try, versus some actions that you're going to take that are going to work out. Your job is to get as much practice as you can, especially when there's doubt. So I want everyone to pause the video right now and give this one a try. Okay, we're back. So the first thing I want you to notice is we better have broken that apart into left side and right side. So you never have to show me this line of simply copying out left side and right side. You never have to. But that is what we are doing. We are breaking it apart. Okay, if we didn't break it apart, pause it. Give it a shot. Okay, we're back. So, if we were to try to go through and manipulate either of these expressions, my first instinct that I want to start to build is going to be to attempt to deal with the side that has the most stuff to it. In general, if you pick the side that looks the busiest, then it's going to give you the opportunity to do the most with it. And so when you're looking up here to try to figure out, do I want to make left side look like right side? Which side do I want to try to manipulate? I would hope that we would select the left side. There's more stuff to it. Okay, if I'm going to play around with the left side, I notice that I have a tan theta on the denominator. And I know that I can replace that tan theta with sine over cos. Now, I'd like you to take a look at that expression that you have, because I wrote it in a very ambiguous way that I hope that we see that I could actually calculate that to be two different things. That is, I could see that green expression and arrive at a value of 1 over cos theta. Because on top, I have sine divided by sine, and anytime I have something divided by itself, well, then I have 1. And so I arrive at 1 over cos theta. However, I could also look at that and say, though, no, but wait a second. The sine over cos is all on the bottom. So if I want to take sine theta and I want to divide it by a fraction, then I need to flip and multiply that fraction. And so my sines divide out and I get a cos. Two different ways. Now, why was that so confusing? Because when you take a look at the fraction lines that I drew in, those fraction lines look equal. So just to write that in again, if I write my expression this way, it can be really confusing because those two fraction lines are the same length. So what I would stress to you, anytime you're going to have fractions within fractions, write your dominant fraction line larger than the others. So, as I go through to write that, I notice that this fraction line, sine divided by cos, is my dominant fraction line. That's the first division that I see. And therefore, when I write that expression later on, I need to ensure that its fraction line is dominant. And so now when you take a look at that expression, there is no confusing what is the top and what is the bottom of the given fractions. On top of that big fraction line, I have sine theta. And underneath it, I have sine theta divided by cos theta. I can now see my fractions within my fraction clearly. And so, if I was then to go through, I could see that I am dividing fractions, so I'm going to flip and multiply. And now I have an opportunity to cross-reduce, because I'll see that my sine thetas will divide out, and therefore I arrive at cos theta, and I love having cos theta. Why? Because what's my right side? It's cos theta, and since my left side equals my right side, it has been proven. So let's keep things going. Let's keep building up our instinct. Let's tackle another one. As I said earlier, I want everyone to pause the video, give this one a shot. Okay, we're back. So this would be one where maybe I look at the very beginning and I'm not sure what I want to do with this one. I look on the left side of my equals and I notice that I have two terms. I look on the right side of my equals and I notice that I have one term, but that term's kind of ugly. So I would argue to you that there is no great way that when you look at this, you go, I can automatically see what I want to do. So we're going to stumble a little bit. And most of our proving of identities will be stumbling. We have some instincts and they lead us down good paths. So I'm just going to manipulate the left side, only because the left side comes first and I read left to right. So maybe I look at that left side and I say, I'm not sure what to do, but I know that I can always replace my tan with sine over cos. And since I just subbed in using my quotient identity, I'm going to quote my quotient identity. Well, now that I have that, my next decision is always made for me. Anytime I substitute in, then I know that my next decision, simplify, which means I need to get a common denominator. This whole thing is going to need a common denominator of cos x. So, I know some of us might want to kind of do something like that and view the sine x as being over 1. And therefore, if you were going to get a common denominator, you would have to multiply the bottom by cos x and therefore multiply the top by cos x. I never want to see that red or that green. We should be okay to jump straight to sine x cos x and then the sine x from the original fraction. So I'm just going to circle that we should be able to see the adjusted fraction here and our original fraction here. Now, okay, I got to that point and I've simplified. And I have nothing else that I can do on that line. But that really doesn't look like the other side. Well, one of the actions I can take can be to unsimplify something. And what's one way that I can go through to unsimplify something? I can factor it. I want you to take a look at the top of that fraction. How many terms do you have? You have 2. And is there something in common in those 2 terms? Hopefully we see that there's a sine x in both of those terms. So I'm just going to go through and delete out all that ugly mess just so we can see everything clearly. That on top I have a sine x cos x plus sine x all over cos x. In my first term, there is a sine x, and in my second term, there is a sine x. then what I'm going to do is I'm going to common factor out a sine x. What would I be left with from the first term? I'd be left with a cos x. What would I be left with from the second term? A positive 1. And now that I have that, I can get down to that point. Okay. Maybe some of us can even see where we would go next. We're one line away. How many terms do I have on the top? We're down to one term, which means that I can do this division. And perhaps you can see that if I divide out my cos x from the sine x, then I have tan. Remember, tan x is equal to sine x over cos x. And so, sine x over cos x is equal to tan x. We've tackled 3 problems where we substituted in for tan. Here's a problem where we can substitute in for sine x over cos x. That gives me tan x times, and now that I see 1 plus cos x, I'm just going to write it in the exact same form, so left side looks exactly as the right. And there we go. Left side equals right side, therefore we've proven that identity. Now, what I want to do is I want to go back to an alternate way that we could have gone through and proven this. My bet would be that if I was to leave you guys, I would have had nobody who would have went through that process. But it's very important for you to see it. So what I want to do now is I want to get rid of a bunch of that. I'm going to imagine that after we worked our way through and we followed my guidance of every time I sub something in, I simplify, then maybe we got stumped right on that last blue line. And we looked and we said, well, there's no other way to simplify that. I can't add sine x, cos x plus sine x together because they're not like terms. Well, when in doubt, if you can't see where to go, jump over to the other side and let's begin to manipulate the other side. Okay, so you look at the other side and you notice you have a tan in there. And so we sub in sine over cos for our tan because we know our quotient identity. I'm going to quote it. That's what I used. Every time you sub something in, your next action is decided for you. So what do? We simplify. So I'm going to now take my sine x cos x and I'm going to expand it into the brackets. And when I expand it into the brackets, I'm going to get sine x over cos x plus sine x cos x over cos x. Now, I know and I'm hoping that actually a really good instinct for us would be to divide out those cos x's. However, we don't want that because look back at the left side. We actually want to have a common denominator of cos x because now that I'm adding 2 fractions together, they both have a denominator of cos x. I can add the tops together and notice we just got down to the left side equaling the right side. A second way to go through and prove it. So don't ever feel like there's one way you have to do it. There isn't. Manipulate one side. If you run into a snag, jump over to the other side and keep working your way through. Okay, here comes the last one for today. So, everybody can see our last identity on our screen. I want to jump in and give it a shot on our own. Pause the video now. Okay, we're back. So, I'm going to walk through as if I was tackling this problem on my own. So, I have to prove this. I know I have to break left side up into right side, or break it up from the right side. And I look at the left side, and that left side just has more stuff to it. So, I'm going to take the left side and try to manipulate it. So I don't need to write down cos squared over 1 minus cos squared theta over 1 minus sine theta. I don't need to write down and copy down the line. But I'm just going to jot that down for a second. Now, I look at both of those and I go, yeah, I have a quotient identity that I've used a lot today. But quotient is what I tend to use when I have sine over cos, or if I have a tan. And when I take a look on that left side, I don't have either of those. But I do have another identity at my disposal. I have the Pythagorean identity, which, remember, tells me that sine squared theta plus cos squared theta equals 1. Now, we may take a look at that and we go, yeah, but we don't have a sine squared theta plus cos squared theta either. But what's very important for us is that since we have already proven this identity, then any manipulations of it are also true. Which means that if I had a sine squared theta, that would equal 1 minus cos squared theta, because I would just get rid of my cos squared. And also, if I had a cos squared theta, then that would equal 1 minus sine squared theta, because I would just get rid of the other. That the blue and red forms of Pythagorean that you see are probably more used than that original gold form. So you take a look at that this time and you notice that that red form could be very useful for us because we know what cos squared. We have cos squared in our identity. So let's use it. So that means that I can replace my cos squared with 1 minus sine squared. Okay, we get to a point, I've substituted in. I'm going to label it because I just used Pythagorean, so a P with a circle. And now I got to try to figure out how to make left side look like right side. Well, there's nothing I can do to really simplify it. Like I could, if I looked at this, break apart my fraction, but that's not going to help, and I definitely can't combine a sine squared with a 1 or a sine with a 1. So, what can I do? Well, if I can't simplify it, then I can unsimplify it. How can I unsimplify? Generally, that means I can factor. Now, perhaps you take a look at that top and the bottom, and you don't see factoring, because we don't see any common factors. And that is true. There are no common factors in top and bottom. However, my top happens to be a pretty special form. I don't want to alarm anybody, but hopefully that we're able to draw back on that top would just be like something like 1 minus x squared. And we should be good that we could factor that top, because 1 minus x squared, that's a difference of squares. And we could factor that into 1 minus x times 1 plus x. You get a little confirmation if you were to read expand the x or the blue, you get back to the blue. And so what that tells us then is I could actually factor the numerator of that big fraction into conjugates. That it would be 1 minus sine theta times 1 plus sine theta. Why does factoring become useful? Because now, how many terms are on top? 1. That means that I can divide out common factors now, and I notice that on top and bottom, I have a 1 minus sine theta factor. When I divide out that common factor, that's going to leave me with 1 plus sine theta. And notice, that was my right side, and so my left side equals my right side. So I just want you to notice a couple of the things that we've used today. Off the bat, we have quotient and Pythagorean identities. Those are our two tools that we can use to sub in to start manipulating identities. After we make that substitution, we've got a couple other key things that we've been able to work our way through. We've had to go through and simplify some fractions. And so in most cases, that simplifying meant common denominators. So to add or subtract some fractions was a key process. Also, we saw two examples where we had to factor. So we had some factoring that we dealt with. Common factoring, some difference of squares, and so on. Keep those two actions in your back pocket along with your two tools, and I think it should be good. Your job now is to get as much practice with identities as you can. Again, they're all instinct. So start training your gut of what leads you down a good path versus a bad one, and I think you're going to find that over time you're going to get much better at proving identities. Jump in and get some practice. Good luck.